What is up, YouTube? It's your favorite math and physics tutor, Matt Physics and Fitness, here with episode 2 of the Multivariable Calculus playthrough. I've been thinking a lot about the series and a few changes I want to make, but before we get into the fun stuff, let's check out our max squad for the week. Okay, here we are. Quiz 3. This is where we left off last time. We got a question wrong, so I'm going to start the quiz. But about those changes to the series, last time I was trying to do a lot of teaching, but the main problem is I don't know multivariable calculus. This is really supposed to be a learning experience for me, so I'm really just going to try to focus on learning it for myself, and hopefully you guys can enjoy watching me along the way. But I don't think I'm going to be trying to do too much teaching. I'll just be talking to myself like normal when I do math. So let's see. F of xy equals ln x squared plus y, g of t equals sine of t minus cosine t, f of g of t, h prime. Again, I remember what we're doing here. We do the chain rule, f prime g of t, g prime of t, normal chain rule stuff, g prime of t, obviously cosine t, sine t, not going to make a derivative mistake like last time. And those are the xy terms specifically. Now, f prime g of t, f of xy. Remember, g of t, this is x, this is y, so this is going to be ln. Ooh, I'm not too confident anymore. ln sine squared t, comma, oh no, plus, and then instead of y, we use negative cosine t, so ln sine squared t minus cosine t, because it's plus negative cosine. So that's our f of t, that's our f of g of t, that's our g prime of t. Oh god, I completely forget now what I'm supposed to be doing. And then I multiply something together. Like this goes to the x term. Oh man, no, but it's the derivative of f prime g of t. I can take the derivative of that, but I don't think it's going to help me too much. Oh no, I'm rusty. I know I'm so slow right now. What do I do? Ah, I thought there was supposed to be a comma here, and then I multiplied two terms together. The x direction, the y direction. Ah, I'm just so confused because this x and y are the same. Ah, I should have watched my last video to see what I was doing. I know I have to take the derivative. This is just f of g of t. I need f prime of g of t. Maybe I'll take the derivative first. Hope that helps. ln 1 over x squared 2x, just 2 over x, plus, oh, but no, see, oh, so this is dx. Oh, maybe I do dx. I do a double, I first do it in terms of x. That's the x partial. And then the y partial is just 1. Maybe I do the x partial times this, and then the y partial times this. Although now here, instead of 2 over x, maybe I use 2 over sine t. Because that's my x term. No, man, I don't even know. I'll do 2 over sine t as my x partial. And I'll multiply that by cosine t, so it'll be 2 cosine t over sine t. And then plus 1 times sine t, so plus sine t. I'm not confident at all, though. 2 cosine t over sine t plus sine t. Let's try it. I could do, instead of 2 cosine, I could do 2 cotangent, right? Let's do it just to keep it simple. And not, I mean simplify, not really simple. Make sure to simplify our answers. instead of cosine over sine cotangent plus sine of t. If this is right, I'll be very happy. It was right? Okay, let's think. What did we do? We took the x partial, we took the y partial, we plugged in our x and y values from here, and then we multiplied those partial derivatives with no x and y terms plugged in with the partial derivatives here. I was thinking about this over the week about why this made sense, and I got a reasonable explanation in my head, but God, if I could explain it right now, I don't think so. What is the speed of v of t? Okay, big thing about speed is it just means magnitude. So if it's negative, you just still view it as positive. Um, I have no idea what this means though. Oh no, I didn't see this in a video. Speed of v of t. There's only one function here, so I have to assume it's a bit easier than what I just did, right? What is the speed of v of t? Is it just like I'm gonna square them all and take the square root. I'm gonna basically just do the Pythagorean theorem and but with three terms and see what happens. The square root of t to the 8th plus 4t to the 6th plus t to the 8th, the big square root on the outside. T to the no, t to the 6th comes out. No, no. No, but I want that to be a t cubed on the outside. Oh, terrible. I don't actually have oh, but is there like a derivative? V of t. What is the speed of v of t? I can take all the derivatives and then add them in quadrature or something. I don't even know. I mean, here a t cubed comes out, or t squared. T squared. Uh, a 4t squared. This is a 6. Ooh, ooh, ooh. What's that? T to the 6th plus 9t. We're gonna go with C. I don't really know why, and then we're gonna look it up. Is this really what I'm gonna go with? Is it really what I'm gonna go with? That's 8t cubed. Don't ask, don't ask, don't ask. A 9? Oh, I don't know. Wow! I can't see a step-by-step solution, right? Because I got it right. Wow, what happened? I just said 8t cubed. God, that doesn't make any sense to me. Not going to question it now. Next question. Let h be a vector valued function defined by h of t equals log 10t sine t. Find h prime of t. That's not that hard, right? It's just you take the derivative of each one separately. Nothing too crazy. Do you need the oh, it's log. Oh, I see. It's a log 10, not I think it's that. To be honest, I don't really understand how. I don't remember how to take the derivative of log, but nice. So you're gonna my lifts this week. I was actually weaker on two lifts. I think it was because I played basketball in the morning and I went back at night and I couldn't get into it. I was so weak. So both of the lifts where I'm wearing that shirt, you'll see I was actually weaker. I think I might have even had more too. I don't know. It's hard to say. We need g prime of t, right? 1, 2, and 4. 1, 2, 4. And then we need f prime of g of t. Delta f of g of t equals this, yeah. Yeah. F prime of g of t. And then you multiply these together in kind of like Evaluate at t equals pi. Yeah, substitute all pi. It's 2 because we need f prime at g of t. So f prime at this number equals this. So 2, -4, 3. And then you multiply like x by x, y by y, z by z. So 2, 1 is 2. -4 and 2 is -8. Let me fix my thing. Let me fix my hand. 2 and 1, 2 and -4 is -8. 4 and 3 is 12. 4, 6. I think it's 6. Let h be a vector value function defined by h of t equals 3 cosine t minus find h prime of t. Okay, and you just take the derivative of each one separately. I think I'm going to get this one right, and then we can look at our incline press. But maybe before that, we'll go over that velocity function. Because I didn't actually know what I was doing over there. 3, -3 sine t, ba, 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 negative, the negative root 4, you can just, oh, no. Yeah, you can just do that as a constant and then treat the function as just square root of t. The square root of t, t to the 1/2, so 1/2 over root t. So, negative root 4. Oh, negative root 4 is just -2. So minus 2 over root t. Minus 2 over root t. I want -3 sine, right? Oh, but it's -2 over times 1/2. Times 1/2. So it's a. So it's a. Also, I think that's the only because this one should be in parentheses, right? That so you can look at just the x term, right? Because derivative of cosine is negative sine. Let's go! Show some. Uh, I don't want to try it again because I just got it right. I just vectored functions, parametric velocity and speed. This is what I need to look at. I don't really want to watch a video though. Up next, multivariable chain rule, multivariable train rule. Let's do a quick video. No, I don't want to take the test. Vector valued function and derivative example. Differential vector valued function. Oh, where's the video? I need a velocity. Parametric velocity and speed. I know I'm proficient. Maybe let's just go. Oh, this is the same question, right? Is this one? Check. Show a step-by-step solution. It's the absolute value of the derivative. I knew that. I knew that. Wait, but why didn't I understand that? How, add them? Equals, you do add them in quadrature. I was kind of right, but you add the derivatives. Did I just not do it very hard? Did I just not try that hard? Let me see. So we add the derivatives in quadrature. Oh no, I have to square these all separately, right? There's two of these, so I'm gonna just do 2. You can bring out a t to the 4th. And you can only bring out a 4. Wow, that's crazy. And that's going to be 8. That's going to be... Okay, cool. You do add them quadrature. Take derivative, add them in quadrature. Makes sense. Because it's just a speed, so you're just taking the absolute value of hypotenuse. Okay, cool. No, not here. Okay, before we get started on quiz 4, let's check out our incline dumbbell press for the week.
Oh no.
60 pounds. I think it was 4 or 5, right? I got 8 last time. It was a tragedy. But I did play basketball that morning, so maybe that's why I was weaker. It's hard to say. Just a partial derivative in terms of y? It's easy. Also, my barbell row, I was weaker this week. It was tragic. I wanted to be stronger for you guys, but it just didn't happen. Hopefully next week I can break my week 1 numbers. Also, something I forgot to mention, I was stronger on the squat, right? 185 by 5. Not too sad about that. Yes, something I don't know. Div of F. Ba, ba, ba. I don't know. What? Number. Check. The formula for divergence in 3 dimensions is x plus y plus z, where p is the component. X of f, q is the y component, and r is the z component. That makes sense. So you take the partial derivative, but only of the resecting components. I can do that. What? So 7xz to the 6th times z. 7xz to the 6th times z to the 7th. Ooh, I'm silly. 0. Oh no. 7e to the 7z, of course. Whew. Whew. I'm slacking a little bit. Here I made a mistake. You can just easily separate this to x to the 7th times z to the 7th. Make it a lot easier. And then you can just treat z to the 7th as a constant, to be honest. That's nice. 7e to the 6th, z to the 7th. I didn't even think about it like that. Y component is 0 plus 7e to the 7z. Here's a vector field. What is the sign of the divergence? I don't know. Negative? Going down. What? Oh, because it's all going in the same direction, maybe? How much the vector field expands or contracts to divergence. Expansion means the positive divergence, contraction means a negative divergence. We can look at the vectors. All the vectors are on the center point downwards. Their y component changes as x changes, but this has no effect on the divergence. Related content. Do I want the intuition? I'll try the intuition, why not? Part 1.
All right, everyone, we've gotten to one of my all-time favorite multivariable calculus topics, divergence. And in the next few videos, I'm going to describe what it is mathematically and how you compute it and all of that. But here, I just want to give a very visual understanding of what it is that it's trying to represent. So I've got it here pictured in front of us, a vector field. And I said before that a pretty neat way to understand vector fields is to think of them as representing a fluid flow. And what I mean by that is you can think of every single point in space as a particle, maybe like an air particle
There's a
or a water
particle that's
particle,
moving
something to
towards
that effect. And
in
so
that
but in
direction.
this
Yeah,
space,
perfect.
have a velocity versus this, and then I'm just going to let it play where each one moves along the vector. So he'll be moving in that direction, but doesn't, elsewhere. I think this is the one.
Okay,
And
okay.
the number of water molecules that are inside that, it doesn't look like the count. The number of
Oh, it doesn't look like the count changes. Ooh. So does positive mean that they're coming in and negative means they're going out?
how
So here they're going out, so they're going to go out of the
playing,
circle.
put
Is
some
that
small
positive or
molecules in there
negative?
and let them flow along the vectors that they flow along. The density inside that region around the origin decreases.
Decreases,
So
yep.
vectors there, and I'll just play for a quick instant.
Yup,
For an instant.
yup.
And one thing that characterizes this field around wave from the origin, and we were to flip them around, the density in that region increases. So these don't diverge away; they converge towards the origin. And that fact actually has some mathematical significance for the function representing this vector field around that point. And even if the vector field doesn't represent fluid flow, so it represents like a magnetic field or a, think about this, if you look at that same kind of outward flowing vector field, is rather than thinking of a decrease in density, imagining that the fluid would have to constantly be repopulated around that point. So you're really thinking of the origin as a source of fluid. And if I animated this better, a whole bunch of other points would be sources of fluid so that the density doesn't decrease everywhere. But the idea is that points of positive divergence, where things are diverging away, would have to have a source of that fluid in order to kind of keep things sustaining.
Positive divergence means that it's kind of pushing a flow out of itself. So you would be like a spring, kind of, that would be a positive thing. It's giving you water, positive. Taking water, negative. Okay, perfect. Easy. Divergence formula part one.
Hello, everyone. So now that we have an intuition for what divergence is trying to represent, let's the y
Partial to
component of
x
the
plus partial to y plus partial to
like
z.
near side, look, things are
X
moving
partial to
potentially
x
where only the x.
component,
So we
y
have key with
partial
the
to y
vector
component.
attached to it. So this here again represents our point. X look is value x because a little bit of case is kind of involved in the formula for the divergence of. Hello again. In the last video, we were looking at vector fields that only have an x component, basically meaning all of the vectors point just purely to the left or to the right with the partial to the first component. Same thing we did saying nothing. So the bottom up. So the y value of your input is increasing as you're moving upwards in space. The value of q, this y component of the output, should also be increasing because it goes from negative to 0 to positive, where maybe you actually have a vector attached diverging
I'm
towards
not
0.
going to be
And once
able to
again,
understand this
the
right
idea of
away.
partial derivative of q with respect to y being greater than 0 seems to.
I think I can do it though. Let's try it. Quiz 4. The positive side of each axis is labeled. Ooh. Graph x squared minus 2 minus y squared. So the y should be going like this, the x should be going like this. The z should not be each. If we move along the z axis, everything should stay the same, right? So like if we take a chop, or our x and y stay the same. I don't even know how to think about that. If our x and y stay the same. Yeah. It doesn't even have a function, a factor of z, so that's why it's only a. I don't even know. Whew. Okay, but the y, as y gets bigger, it should go down for sure. As y gets bigger, it should go down. As x gets bigger, it should go up. So I'm pretty sure it's just 1. It's just a. Okay. Don't really know, but okay. X partial, the first one. Negative sign. Negative sign is positive sign. Y partial, the second one. The y just goes away. Oh, and then you add them together? What? Sine x plus negative sine of x. You know what that is, right? Woo! Boom, boom, boom. No, let me take it in. Oh, what was next? Lesson 10? Even is lesson 10. Let's go. Let's go. Oh, what is the divergence of f at 0, 1? Oh, it's 0. It's just 0. Don't even worry about it. What? Oh, let's see. Oh god. Okay, let's see. I just don't understand as z changes. So maybe I think z is not in this function. Yeah, it's a function of x, y. I need to see a function of x, y, and z to see what that would look like. Let's see. X looks like cosine. Looks like a cosine. Y looks like also cosine. No. Y looks like negative y squared. Yeah, y looks like negative y squared minus y squared. Cosine x minus y squared. Ba 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 ba. If we're a dot in this, are we going to be gaining fluid or losing fluid? They're kind of bigger over here, but I feel like it's kind of a consistent flow of fluid, but I feel like it's. I want to say the density will be increasing because it's going in quickly and leaving slowly. That's what I want to say. So it would be gaining fluid, which means it's negative. Woo! Nice! Because the things coming into it are bigger than the things going out of it, so it's negative. The divergence is negative. The divergence is positive when the stuff leaving the circle is big. That makes sense. Divergence leaving is big. Diverge. df dx. df dx. This is not. This is just the derivative of the whole function. This is the whole partial for x. But you do still comment it off. Da da da. Nope. Da da da. Yep. Da da. Yep. Woo! Here's a vector field. The divergence is positive. Woo! What? What? No! Stop! I have to take it again? Again. Give me 100. Okay, they're all the same. 0. The positive sign of each axis is labeled sign of x, not that one. The positive. They almost tried to get me. It's this one. Yep, yep. It's that one. That looks like a negative sign, but the x is going the other way. I don't like that. No, give me some divergence. I don't think they were gonna 2VW, 2VW00. Yep. Yes. F at pi 0, pi over 2. That's what I'm talking about. First, we take the x derivative of the x partial. Cosine x. God, how long is this taking? They're supposed to be 45-minute episodes. Maybe I should have taken a done a lift after that. Is that correct? Oh, I completely forgot about that. Cosine x, the y partial. Oh my god, that's 0. Oh my god, the z partial, that's also 0. That's crazy. So all of these are 0, so then you add them all together. But so it's just cosine of pi. It's cosine of pi, guys. -1. It's -1. Yeah. -1. Whoa, are they the same size? I can't even tell. They kind of look like the same size. I think it's 0. Hopefully, cross your fingers. So, what is it? Is it negative? Ah, no, but these ones are bigger than these. God dang it! Is this one? This one is 0. This one is not 0. This is so. I'm so angry. This one's negative. Okay. This one's positive. This one's 0. This one's negative. Do it again. Do it again. This one's positive. Yeah. This one's 0. Whew. This one's this one's negative. Yeah. Woo! This one's positive a little bit. Woo! Okay, perfect. Figured it out. Let's check out our snatch for the week. Let's go. 115 by 1.5. Better than last time. I only did 105 for 2 last time. I was happy with 115. I actually went once during the week and I got 1 for 2 and I tried 115 and I couldn't even touch it. So I was happy I got that right actually. You can hear my dad laughing in the background as I missed it. What a guy. What is this? Positive? Right? Oh, what is the sign of the curl? Ooh! I remember curl. I forgot how to do it, but I remember it. There was like a matrice or something involved. Ooh. Oh, I think it's negative. It's yeah, of course. Let F be a 2D vector field. Is the expression gradual curve of a scalar field a vector field undefined? Oh, I don't know. I completely don't know. Oh. The gradient, which takes a scalar field and gives a vector field, can be written in 2 ways. Yeah, because it gives a vector field, right? So the expression, yeah. Yeah, I don't know. I don't know this. Finding gradients. Let's do it. Let's learn a little bit. Still in Unit 2. Hey. How many more do we got? We got 2 more lifts. We might be able to get, not through, I doubt we're going to get all the way through Unit 2, but we can give it a try. Gradient. Let's learn about gradient. Finding gradients, I'm proficient. Oh, was this? Oh, finding gradient. Oh, God.
So it's like how many dimensions do you got?
What
Because if you
was
had a
this? It
three-dimensional
was just like we were given like constants. We were given like a direction. I thought it was like a directional derivative, but it's not.
function, that would mean that you should treat this like it's got 3 different operators as part of it.
Oh, I think this was right before directional derivative, right? Yeah. Okay. Cool. No, I need this one, visual curl, but I need not the 2D curl intuition.
Hello, everyone. So I'm going to start talking about curl. Curl is one of those very cool vector calculus concepts, and you'll be pretty happy that you've learned it once you have, if for no other reason because it's kind of artistically pleasing. And there's 2 different versions. There's a 2-dimensional curl and a 3-dimensional curl. And naturally enough, I'll start talking about the 2-dimensional version and kind of build our way up to the 3D one. And in this particular video, I just did one associate time. A particular example, this particular vector field that I pictured. And at any given moment, if you look at the movement of one of these blue dots, it's moving along the vector that it's attached to at that point. Or if that vector's not pictured, you know the vector that
Are we
would be attached to
measuring
the vector.
how much
And this is kind of a feel for
they're
what's going on in this
curling?
entire flow. I want you to notice a couple particular regions. First, let's
So
take
if they're moving in a straight line, it's probably 0, right? No curl. If they're saying it's probably no curl. But the second they have any kind of curve to them, you're probably measuring like how close to a circle it is, right?
Kind of around here. And just kind of concentrate on what's going on there. And I'll go ahead and start playing the animation over here. And what's most notable about this region is that there's counterclockwise rotation. And this corresponds to an idea that the vector field has a curl here. And I'll go very specifically into what curl means. But just right now, you should have the idea that in a region where there's counterclockwise rotation, we want to say the curl is positive. Whereas if you look at a region that also has rotation, but clockwise going the other way, you think of that as being negative curl. Here, I'll start it over here. And in contrast,
right-hand
there's no
rule.
rotation, where like at the center here, you have some points coming in from the top right and from the bottom left, and then going out from the other corners. But there's no net rotation. If you were to just put a, if you were to put
that's
a
0.
water,
There's no net rotation.
These are regions where you think of them as having 0 curl. So with that as a general idea, clockwise rotation regions correspond to positive curl, counterclockwise rotation regions correspond to negative curl, and then no rotation corresponds to 0 curl. In the next
Because
video,
they're still curving, but
the
they're not
underlying function
rotating.
defining the vector field.
They're
How we
just
start
going
looking at the
on
partial differential
asymptote.
information of that function to quantify this intuition of fluid
So it's
rotation.
not really a
And what's neat is that
curl.
it's not just about fluid rotation, right? If you have vector fields in other contexts and you just imagine that they're a curl, even though it's more.
Okay, so it's just a dot curling and counterclockwise is positive. That's the idea. I want the formula.
So after introducing the
I mean, let's start this. Let's just try it. 0. 0. What? It's all going like this. At the center of the vector field, there's no rotation, I thought. What? Okay, positive? I don't know. What? Negative? This is clockwise? Oh, I guess. Yeah, clockwise. That kind of makes a little bit of sense. At the center, the vector field is negative. All the vectors are in the center point down to the right, but the vectors on top. Oh, on top are bigger than here. Oh, so you would think that that one is dominating. Okay, fair enough. I'm with it. So now this one is dominating, so that is clockwise, right? This is still counterclockwise, so it's positive. Okay, cool. This one has to be 0, right? Gotta be 0. Woo! Formula.
Introducing the idea of fluid rotation in a vector field like this, let's start tightening up our grasp on this intuition to get something that we can actually apply formulas to. So a vector field like the one that I had there, that's 2 dimensional.
Well, let me think. Counterclockwise is positive, right? So that means x positive, y positive is
is given by a function that has a 2-dimensional input and a 2-dimensional output. And it's common to write the components of that output as
it's like if we move in the x direction, our y goes up. If we move positive x, and y goes up.
And what I want to do here is talk about this idea of curl.
Positive,
and write it down as just curl.
If it goes down, that's negative, maybe?
Which takes in the same inputs that the vector field does. And because this is a 2-dimensional example, I might write, just to distinguish it from 3-dimensional curl, which is something we'll get later on, 2D curl of v. So you're kind of thinking of this as a differential thing, in the same way as like you want it to give you a positive number. That should mean. And a good way to understand this 2-dimensional curl function and start to get a feel for it is to imagine the quintessential 2D curl set 0. You have one pointing straight down and is greater than 0. So this function q, so in terms of the functions, what that means is this vector to its right, whatever point it's evaluated at, that's going to be q is greater than 0. So this function q that corresponds to the y component, the up and down component of each vector, when you evaluate it at this point to the right of our xy point, q is going to be greater than 0. Whereas if you evaluate it to the left over here, q would be less than 0. In our kind of perfect.
So this is going to be a partial derivative, pretty much. Like as x goes up, does y go up?
Positive example. And then these bottom guys, if you start thinking about what this means for, you have a rightward vector below and a leftward vector above. The one below it, whatever point you're evaluating that at, p, which gives us the kind of left.
And this is y. The derivative of y. As we go down, we want x to go up.
The first component of the output would have to be positive.
Right. As we move down in the y direction, we want our x component to go up.
Whereas p, if you did it on the left and right points, would be very specific pieces. So we want positive q. What derivative corresponds to positive 2-dimensional.
Exactly right. Yeah.
And in fact, it turns out these guys tell us all you need to know. We can say as a formula is equal to respect to y, because I want with this right here the formula for two-dimensional curl, which basically you can think of it as a measure at any given point. You're asking how much does the surrounding information to that point look like this setup, like this perfect counterclockwise rotation setup. And the more it looks like this setup, the more this value will be positive. And if it was the opposite of this, if each of the vectors was turned around and you have clockwise rotation, each of these values will become the negative of what it had been before. So 2D curl would end up being negative. And then
But this is important. This is the x derivative on the y component. So as the y component changes, what happens to the x derivative? As the x component changes, what happens to the y derivative? But we want as the x component changes. I wanted y to go up. This is the dq. The ooh ooh. Oh, but q is the y. Yeah. So as we move in the x direction, we want q to go up. As we move in the y direction, dy, we want p. As we move up in the y direction, we want p actually go down because that's negative in the x direction. Okay.
in the next video, I'll show some examples of what it looks like. So I spent a couple videos laying down the foundation for what three-dimensional curl is trying to represent. And here, I'm going to go ahead and talk about how you actually compute it. So 3D curl is the kind of thing that you take with regards to a three-dimensional vector field. So something that takes in a three-dimensional point as its input, and then it's going to output a three-dimensional vector. And it's common to write the component functions as p, q, and r. So each one of these is a scalar value function that takes in a three-dimensional point and just outputs a number. So it'll be that same 3D point with the coordinates x, y, and z. X, y, and z. So when you have a three-dimensional vector field like this, the image you might have in mind would be something like this, where every point in three-dimensional space has a
Yeah.
vector attached to it. And when you actually look at it, it's
Just imagine that,
in
guys.
principle, all that's really happening is that each point in space is associated with a vector, and the point in space is the input, and the vector is the output.
This
and
looks like it's convert.
And
Oh,
naturally, because
yeah.
between the three dimensions of the input and the three dimensions of the output, we have 6 dimensions going on. The picture that you're looking at becomes quite messy. So the question is, how do you compute this curl value that I've been talking about? Curl.
Let's look at
of
the
your vector
formula,
value function.
guys.
And just as a quick reminder, what this is supposed to be is you're going to have some kind of fluid flow induced by this vector field, where you're imagining like air flowing along each vector. And what you want is a function that tells you at any given point what is the rotation induced by that fluid flow around that point. And because rotation is described with a three-dimensional vector, you're expecting this to be vector valued. It'll be something that equals a vector output. And if that doesn't make sense, if that doesn't quite jive, maybe go check out the video on how to represent
I can't
rotation
even
with a vector. So what you have
think
here
about
is something that takes as its
three-dimensional
input
curl,
x, y, and z,
three-dimensional
takes a three-dimensional
rotation.
point, and what it outputs is a
Maybe
vector
he does a good
describing
job
rotation.
explaining.
And there's actually another notation that's quite helpful when it comes to computing this, where you take nabla, that upside-down triangle we used in divergence and gradient, and you imagine taking the cross product between that and your vector v. And as a reminder, this nabla, you imagine it as if it's a vector containing partial differential operators. And that's the kind of thing where when you say it out loud, it sounds kind of fancy. A vector full of partial differential operators. But all it really means is I'm just going to write a bunch of symbols, and this like partial x is something that wants to take in a function, a multivariable function, and tell you its partial derivative. And strictly speaking, this doesn't really make sense. Like, hey, how can a vector contain these partial differential operators? But as a series of symbolic movements, it's actually quite helpful because when you're multiplying these guys by a thing, it's not really multiplication. You're really going to be giving it some kind of multivariable function like p, q, or r, the component functions of our vector field, and evaluating it. So just as a warm-up for how to do this, let's see what this looks like in the case of 2 dimensions, where we already kind of know the formula for two-dimensional curl. So what that would look like is you have a smaller, more two-dimensional, just partial x, partial y, del operator. And you're going to take the cross product between that and a two-dimensional vector that's just the component functions p and q. And in this case, p and q would be these diagonal components and multiplying them, so that would be a duplicated point. So when you compute something like this, the cross product, you typically think of it as taking these diagonal components and multiplying
Cross
them. So that
product.
would be your partial x, quote unquote, multiplied with q, which really means you're taking the partial derivative of q with respect to x. And then you subtract off this diagonal component here, which is, let's see, so partial, oh, sorry,
That's
this
a
would be a y.
y, yeah.
Y. So, okay, sorry about that. You're taking partial y of p, and that's what you're subtracting off. So partial y of p. So just the partial derivative of that p function with respect to y. And hopefully this is something you recognize. This is the two-dimensional curl, and it's something we got an intuition for. I want it to be more
So
than
these
just
are
a formula.
not derivatives
Kind
of any
when you
function.
take
This is
that
just
del
the
operator,
idea
that
of
nabla
big
symbol, and cross product with the.
This is just a
function
matrix
itself,
of
you can use it as a
derivative
curl. Now when we do this in the
operators.
three-dimensional case, we're going to take a three-dimensional cross product between this three-dimensional vector-ish thing and this three-dimensional function. And that would be a good time, by the way, if you're not terribly comfortable with the cross product or how to compute it or how to interpret it and things like that. That would probably be a good time to go find the videos that Sal does on this and build up that intuition for what a cross product actually is and how to compute it. Because at this point, I'm going to assume that you know how to compute it because we're doing it in kind of an absurd context of partial differential operators and functions. So it's important to have that foundation. So the way you compute a thing like this is you construct a determinant.
Yeah, really important to have that foundation.
Of a certain 3x3 matrix. And the top row of that is all of the unit vectors in various directions of three-dimensional space. So these I, j, and k guys, I represents the unit vector in the x direction. So that would be I is equal to, x component is 1, but then the other components are 0. And then similarly, j and k represent the unit vectors in the y and z direction. And again, if that doesn't quite make sense, why I'm putting them up there or what we're about to do, maybe check out that cross product video.
These are
so
unit
those top rows as vectors. And this is kind of the trick to computing the
fine.
cross product because, again, it's like, what does it mean to put a vector inside a matrix? But it's a notational trick. And then we're going to take the first vector that we're doing the cross product with and put its components in the next row. So what that would look like is the next row has a partial y and a partial. Oh, sorry, God, I keep messing up here.
X, Y, Z.
You do whatever the first component is first, and then the second component second, and the third component the z, partial z. I don't know why I'm making that little mistake. And then for the last row, you put in the second vector, which in this case is vector value function p, q, and r. P, which is a multivariable function, q, and r. And first, it's worth stepping back and looking at this. This is kind of an absurd thing. Usually, when we talk about matrices and taking the determinant, all of the components are numbers because you're multiplying numbers together. But here we've got like a notational trick layered on top of a notational trick. So
you
that one
like
of the rows
block
is
this one
vectors, one of
off?
the rows is
And
like
you
partial
do like
differential
this
operators,
or
and then the last
something?
one, each one of these is a
Like
multivariable
this
function.
minus
So
this,
it
and
seems
then
like it's
like
absurd convoluted as far away
this
from a matrix full of
minus
numbers
this,
thing
and
as
then
you can
like
get. But it's actually very helpful
this
for
minus
computation
this, something
because
like
if you go
that.
through the process of computing this determinant and saying what could that mean, the thing that pops out is going to be the formula for three-dimensional curl. And at the risk of having a video that runs too long, I'll call things in here, but continue going through that operation in the next video. See you then.
Aw, I'm not done yet. I think maybe I'll watch this video, check out the barbell row, and then I'll start the quiz.
So I'm
Let's try to
explaining the
get this
formula for
quiz
three-dimensional
down.
curl, and where we left off, we have this determinant of a 3 by 3 matrix,
That'll
which
be the
looks absurd
last
because none of the individual components are actual numbers. But nevertheless, I'm about to show how when you kind of go through the motions of taking a determinant, you get a vector value function that corresponds to the curl. So let me show you what I mean by that.
I didn't know I was gonna have to
Determinant,
learn how to
the guy
take
we
a
have,
determinant
which would be in
again.
the upper right. You start by taking this upper left component and then multiplying it by the determinant of the submatrix. The
I
submatrix whose
knew
rows are
it.
not the row of I and whose columns are not the row of I. So what that looks like over here is we're going to take that unit vector I and then multiply it by
I
a
dy
certain determinant. And
dr.
what this subdeterminant involves is multiplying this partial y by r, which means taking the partial derivative with respect to y of the multivariable function r, and then subtracting off the partial derivative with respect to z of q. So we're subtracting off partial derivative with
Where's my
respect to z
mouse?
of the multivariable
Can't
function
find it.
q. And then that. So that's the first thing that we do. And then as a second part, we take this j and we're going to subtract off. So you're kind of thinking plus minus plus for the elements in this top row. So we're going to subtract off j multiplied by another subdeterminant. And then this one is going to involve, this column that it's not part of and this column that it's not part of. And you imagine those guys as a 2 by 2 matrix. And its
And then
determinant
you
involves
do
the partial derivative with
plus
respect to
minus
x
plus
of
again,
r. So
right?
that's kind of the diagonal. Partial
This one we do
x
plus
of
minus.
r. And then subtracting off the partial derivative with respect to z of p. So partial z
Yep,
of p.
yep.
And then that's just 2 out of 3 of the things we need to do for our overall determinant. Because the last part we're going to add that top
Add
right component
k
multiplied
times
by the the submatrix whose columns involve the column it's not part of, and
dq
whose rows
dx
involve the rows
minus
that it's not part of.
dpdy,
So
right?
k multiplied by the determinant of this guy is going to be, let's see, partial x of q. So that's partial x of q minus partial y of p. So partial derivative with respect to y of the multivariable function p. And that entire expression is the three-dimensional curl of the function whose components are p, q, and r. So here we have a vector value function v, whose components are p, q, and r. And when you go through this whole process of imagining the cross product between the del operator, this nabla symbol,
Now
and
I'm just
the,
kind of
the
confused
vector
about what
output
they're
p, q,
asking
and
for
r,
the
what you get
ijk,
is this whole expression. And here we're writing it with
they
ijk
want
notation if you were writing it as a column vector.
the constant
Right, so
value.
some of these guys. But if you're writing
Maybe
it
the
as a column vector,
ijk
it would
are
look
like
the curl of your vector value function v as a
a
function of x, y,
direction.
and z
No, I don't think
is
so
equal
because
to.
they're units.
And then what I put in for this first component
Anyways,
would be what's up there. So that would be your partial with respect to y of r minus partial of q with respect to z. So partial of q with respect to I, j, and k. Slightly different. What's happening with these other guys is kind of similar, right? We'll try to sit down long, but it doesn't take that long. And it's certainly much more fault tolerant than trying to score p, q, and r and walk through that process in a more concrete context. So let's go ahead and work partial x, partial something funky. And then we're taking that shows up there as this function of x0. Usually if you're, that's the curl of the function. And in general, that's how you do it. You would take a look at
they
the weight
just
of your
kind of
function
use
as negative
those
x.
as placeholders for like x direction, y direction, z direction. Okay, let's go for it. Let's go for it. Before we start the quiz, check out the barbell row. I don't know what happened that set. I definitely had more. I definitely could have hit 5 or 6. Yeah, I was feeling fatigued. I actually did a set after that where I did hit 6, but they weren't the prettiest reps I've ever had. I don't know why I was so weak on that day. I think it was. I don't know. Hopefully next week will be a bit stronger though. But I think we're ready for quiz 5. Okay, so this is where I don't understand because it seems like the curl was kind of like a two-dimensional thing, right? Oh, no. The two-dimensional curl was kind of simpler, right? It was like the x derivative of this one, which would be interesting. Oh no. What is this? Would be gotta use the product rule? No. 2 ln xy plus 2x 1 over x. It will be 1 over xy times y. Plus 2? Seems right to me. And then the y partial is just going to be 0. So I think it's just this. I doubt we're gonna get this quiz right on one try. I don't think we have it. 2 ln xy plus 2. Yes. Oh, wow, this is still the old quiz. Perfect. Okay, this is perfect. Okay, this is what I want. I don't know why the three-dimensional has these components and the two-dimensional doesn't. Kind of confusing to me. Also, this should be a minus sign, right? So we should put a minus. Let's see here, something like that, just to remember. If it's plus minus plus. Be quiet. Be quiet. Can I not make it be quiet? Really? Okay, let me see. So it's we cross this one out, and then it's like let's just do like P Q. What was it? P Q and R? I hope it was. So we got like dr dy minus or dq dy. No. Dr dy minus dq dz I minus j. Oh no, I don't know if I know this. dp dz minus dr dx. Because again, this is the y component, so we don't use the y theorem. This is the x component, so we don't use the x term. Plus k. I can give these all hats just for fun. Because they're vectors, unit vectors. And then this one would be dp dy, right? No. dq dx. dq dx minus d dp dy. Okay, this is what I think we got. Let's try it. dr dy is 0. dq dz is y cosine z. Nice. dp dz is negative x sine z. dr dx is 0. Do we ever get on dr dz? No, we don't, right? Because that's the z partial. And it makes sense, because on the two-dimension, you never take the partial of the direction you move in. So that does kind of make sense. dq dx is 0. And dp dy is 0. So that one's 0. That one is negative x sine z. That one is negative y cosine z. Ba ba ba. Negative y cosine z. Negative x sine z. 0. Oh, this one was negative, right? So positive. Cross your fingers. What? If it's negative, I'm going to cry. What? It's plus? I need a hint. It is plus. Wait, I got lied to. The video definitely said minus, right? I thought it was minus too. Okay, we'll assume it's plus right now. We'll assume it's plus. Pretty sure I got lied to though. Go back and watch the video and see if it was a minus sign or a plus sign, and see if you guys understand what that was. Because I don't really know if I do. What is the sign of the curl? It looks like these ones are dominating, so it's moving it I don't even know. Maybe counterclockwise? Maybe positive? Okay, we'll try the quiz one more time, and then we'll end it off with the max deadlift. Let's see what we got. Quiz number 5. If we got this quiz right, we actually got more quizzes done in this episode than last time. That would be pretty funny. What is the curl at negative 2 comma 3? Ooh, we can do this. Okay, guys, let's lock in here. This is what we do. This is where we do it. First, we do. Oh no, we do dx dy first. Yeah, minus dy dx. Ooh, I don't know. Dx dy. Right, because you wanted a y as we move in the x direction with the y one to go up. So is the change in the change in the y value, the change in the y component as we move in the x direction should be positive. So yeah, dx dy is positive. So 1 plus 3y squared minus dy dx minus 4x squared, 3y squared, 9, 27, 28, minus negative 2 squared is 4 minus 16. 12. Going for 12. Woo! Hey. Sign of the curl. This has to be 0, right? It's got to be 0. Yes. Woo! Okay, we're going to assume it's plus this time because we got screwed over last time. Oh god, I should have kept that little. No, we need to be able to figure it out every time. Just to make it a bit easier as we go. P, Q, R, D, R, D, Y, minus. You see, I don't know, I don't know. Da da da. Okay, let's try it. dq dy, 2y. dq dz. Whoa. Whoa, 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 whoa. This is the first one. It's y. This is an r, right? Yeah, this should be r. Oopsies. Oopsies. dr dy, 0. dq dz, also 0. Nice. dr dx is 1. dp dz is also 1. 1 minus 1. That's also 0. dq dx, that one is 2x. Yeah, I can barely even your hand right. It's terrible. Plus 0, minus 0. Okay, I think it's 0, 0, and 2x. Let's go for it. 0, 0, 2x. And they have a plus sign here, right? Yeah. Oh, I don't know. Is the expression delta divergence is just a value, right? The change in divergence, a scalar field, a vector field. It's a scalar field, right? It's just a divergence doesn't really have a direction, right? It's just scalar. Let's go for it. Let's see what happens. No, it's undefined. Oh, terrible. Maybe we'll look at that one next time. I'm happy with our calculations today, though. If you get this one right, we're definitely we're going to the deadlift to call it. I was stronger on the deadlift too. Didn't have my straps, still got 3 reps, and I was able to go a lot more touch and go than last time. Last time I really had to rest between the reps. If you saw that, I gotta get. I'm so mad about that incline press. I need to get a strong incline press for next week. Still angry about that. Let's label these again. B, Q, R. I'm trying to like visualize it in my head. I'm so confused. And it's just because in the Matrix, this is on top of this. So I'm getting so lost. Uh, okay. dr dy is 2. dq dz is 0. dp dz is -1. dr dx is 0. So 2, -1. dq dx is -4. dp dy is 1. But it's minus, right? It's -1, -1, -1, -5. I think you guys saw what I was trying to do there. So 2, -1, -5. Either way, I think we're going to the deadlift after this, but if we're right, we'll be happy. If we're wrong, we'll have to see what we can do next time. 2, -1, -5. Come on, cross your fingers. Let's go! Okay, perfect. Ended off with the deadlift. See you guys next time.